Hi, everyone. I'm going to go through homework 5, and then later tonight, the practice exam will be posted. Um, I don't know how late, but it'll be posted tonight. So look for that. Anyway, our first uh, problem says that a constant force is applied to an object, causing it to accelerate at 7 meters per second squared. 7 meters per second squared. And F is equal to ma. This problem is actually super simple. If we double the force, we double the acceleration. That's simple enough. So our acceleration will be 14. If you double the mass, now our acceleration is F over m. So if this becomes 2m, the acceleration becomes half. So we get half the acceleration if you double the mass. If the force and the mass are both doubled, then we get the same 7 meters per second. And finally, if the force is doubled and the mass is halved, so 1/2 over 1/2, the 2 comes up and you get 4 times the acceleration. That's all. I just want you thinking about constant forces and what happens with them. All right. Now in a lab, you propel a cart with 4 known forces while using an ultrasonic motion detector, and you're given data of F and A. Now, remember that when we graph something, if we apply a linear trend line, that trend line is y of x is the slope m of x plus b for a linear trend line. The slope is the change of y over the change of x, and b is simply wherever this line happens to cross when x is 0. So it's the intercept. What we're asked to do is if we want to graph the data to determine the mass. So F equals ma. To find m, we would do F versus A. F would be on our y, A would be on our x axis. So the horizontal axis or the y-axis would get F, the vertical would get A, and none of the rest of this would be used. Why? Because it is a linear relationship between F and A, or F and M. Another data point we could reasonably add would be 0, 0. And the reason for that is when the force is 0, the acceleration should be 0 as well. No force, no acceleration. We don't necessarily know any of those. And then finally, graphing this, that straight line, that linear line, that slope is our mass, because that slope is F over A. It's the change of F over the change of A. And therefore we have a constant mass of 0.56 kilograms. That's all. I just wanted you to think about how you graph things and make sure you guys were all good on that and that you understood how to graph things. Now this one's a little bit different. We have Zach who's in an elevator. So he's standing in an elevator. This is our Zach. And if we draw a free body diagram on him, he has a normal force up and mg down. Before the elevator starts to brake, A is 0. It's just not doing anything. It's moving with constant velocity, and constant velocity implies that A is 0. The velocity is not changing, therefore there's no acceleration. This is his weight vector. And so we can say ma is n minus w, and that's 0. So the normal force is his weight. And what is his weight before it starts braking? Well, if he's 85 kilograms, his weight is mg, which is 85 times 9.8. And that gives us 85 times 9.8 gives us 833 newtons, around there. 830, 830. When it begins to break, now, in order to figure out the acceleration, remember that acceleration is the change of v over the change of t. And so it was descending at 12 meters per second, and it took 2.7 seconds. So this is v final minus v initial over t. V final is 0. It comes to a stop. And v initial was 12 meters per second. And this was 2.7 seconds. So our acceleration is negative or down 12 divided by 2.7, 4.444 meters per second squared. Now that we know that, what we can do is we can come back to this, okay? And what we want is we want to find what is his weight while the elevator is braking. So now, if we get rid of this, A is no longer 0. A is now negative 4.44. We want his weight. Add weight to both sides, subtract MA from both sides. And what we get is we get the normal force minus MA. Now, did I do? Well, letting n equal mg, okay, mg minus ma, or I'm sorry, I'm messing this up weirdly. Since a is negative, let's do this. Let's flip a down. A is 4.44 now. So MA is mg minus, well, let me take that back. MA is his weight minus his normal force. So his weight is MA plus his normal force. And if we assume the normal force is mg, then we get MA plus mg, what the normal force was before he started braking. That means that we get MA plus G, and his mass is 85 kilograms. So this becomes 85, 4.44 plus 9.8. I flipped it so that A was down to get that. So I get 85 times 4.44 plus 9.8, or 1,210 newtons. This was B, or 1,200 newtons, 1,210. All right. We had to assume that his normal force was mg in this, what it was before. I'm not really sure about that, but that's how this problem's done. If we were to solve for the normal force, we would find that the normal force was his weight minus MA, and his weight is mg minus MA. So his normal force should actually be, should not necessarily be mg. His weight should be mg, but his normal force will be about half of his weight. It's a weird question. I think they got it wrong, but yeah, that's me. All right. Now we're going to talk about friction. And the force of friction comes in two varieties: static or kinetic. Static friction, you're not moving. It opposes the net force if there were no friction. So it goes in the opposite way, whatever the net forces are, when it's not, or if there were no friction. Kinetic is only when you're moving, and it opposes whatever direction your velocity is. So it opposes the direction of your velocity. They both have the same form, mu n. For a flat surface, a block would have a normal force of mg. because normal force is up, mg is down, A is up, but 0. On an incline, your normal force is up, but your weight in the direction perpendicular to the surface is mg cosine. So on an incline, your normal force is mg cos. On a flat surface, your normal force is mg. And this is AY, of course. Can't leave the surface. So what we do is, if it's static friction, we figure out what the forces are without friction involved, and then we put that vector opposite the net force. If it's kinetic, if it's moving, we put that vector opposite the velocity, and it's mu n. And then if it's on a flat surface, n is mg. If it's on a incline, n is mg cosine. So what we have is Bob is pulling a 30-kilogram filing cabinet with a force of 200 newtons, but it will not move. The static friction force between the filing cabinet and the floor is 0.8. So if I were to draw this, he's pushing it with a force of 200 newtons. It has a normal, it has an mg, and it's not moving. So we have a static friction force that is mu static n. And they gave us what that was. However, if it's not moving, if A is 0, static friction is a variable force. It has a maximum, and the maximum it can be is mu s mg in this case. But anything less than that, it's not going to move. So any force you push, if it's not equal or greater than mu s mg, it's not going anywhere. So his push force was 200 newtons. The static friction force, if it's not moving, is equal to the force that he's pushing. The maximum it could be, so the maximum it could be, we were told 0.8 is mu, 30 kilograms. So 0.8 times 30 times 9.8. That is the maximum this could be. 30 times 9.8 times 0.8 is about 235 newtons. So if he pushes with 200 newtons, it doesn't go anywhere. If he pushes with 234.9999 newtons, it doesn't go anywhere. The static friction just completely stops it from moving. You have to at least push it with 235 newtons of force to get it to move. So the static friction force when you push with 200 newtons is 200 newtons. It cannot move. All right, that's good. All right, now we have kinetic friction. So a 1,500 kilogram car skids to a halt on a road with mu k is 0.50, has no units. How fast was the car traveling if it leaves 45-meter long skid marks? Okay, so X initial was 0, X final was 45 meters. We need to know V initial. What is V final? 0. It skids to a halt. The last thing we need, if we look at these, is we either need time or we need acceleration. Well, we can get the acceleration by doing a free body diagram, and that's why we do it. So we have 0, 45, 0, unknown, that's what we want. Unknown, unknown. We're not going to use t. So what we'll use is v final squared minus v initial squared is 2a x final minus x initial. And we're going to solve for A using free body diagram, and then we're going to solve for V initial to answer the question. So if you're skidding, you have a normal force up, you have a weight down, and the only force acting on you as you're braking to a halt is the force of kinetic friction. So the force of kinetic friction. That is mu n, mu kn. Our acceleration, we're going to assume is that one. So if I write the y, it's n minus mg, but we already know that, and it can't leave the surface, so n is mg. In the x, we have negative, because it's opposite our acceleration, negative n mu n, which is negative mg. Cancel these, and we get that a is negative mu g, or a is negative 0.50, or a half, times 9.8. And that gives us 0.5 times 9.8, negative 4.9 meters per second squared. Now we want to solve for v initial. V final is 0. I'm going to go to a new page. So we have v final squared minus v initial squared is 2a x initial, or x final minus x initial. This is 0. We're solving for v initial. Move the negative sign over, so I get negative 2a x final minus x initial. But remember, our x final was 45. Our x initial was 0. Our a was negative 4.9 meters per second squared. We're going to end up taking the square root of this, and we'll use the positive. So we get negative 2 times negative 4.9 times 45 minus 0. Or the negative signs go away, and I get 2 times 4.9 times 45. Take the square root of that answer, and I get 21 meters per second. So in this problem, I had to use a free body diagram to figure out that the acceleration was negative mu g. Once I had that, I just had to set it up as a constant force, 21 meters per second. Okay, and that's it. The other thing to learn from this is kinetic friction always opposes the direction that we're going. We were going that way, so kinetic friction works in the opposite direction. I chose A to be in the same direction we were moving so that it would be negative. Otherwise, I would have had to flip these in order to get a positive number. It's not a big deal, but just make sure that you don't get weird negative signs. Now, this one we kind of did already on the worksheet, but now we have different angles. We have an angle of 20 degrees and an angle of 30 degrees. So this is T1, this is T2, 20 and 30. And they're holding this mass up. Now, if I break these, I'm going to call this angle 1 and I'm going to call this angle 2. If we break these, we get T1. This is the sine of theta 1. And this is the cosine of T1. Cosine theta 1. It's that part of the triangle, and the triangle's hypotenuse is T1. This one is T2 cos angle 2 and T2 sine theta 2. And then finally we have mg down. I'm going to choose up to be my AY, and I'm going to choose to the right to be my AX. They are both 0 because it's not moving, but I need to be able to write them. So MAX and MAY. Both are 0 because it's in equilibrium. And I get T2 sine theta 2 minus T1 sine theta 1. And I get T1 cos theta 1 plus T2 cos theta 2 minus mg. And now I have to do some really annoying algebra. I have to solve this for, I want T1. So let's solve this for T2. So on this page, I get T2 cos theta 2 is equal to mg minus T1 cos theta 1. Remember, theta 1 is 20, theta 2 is 30. degrees, and M is 1400. Now, divide both sides by cos theta 2. And I don't necessarily need to solve this quite yet. I could, but my other equation is T1 sine theta 1 is T2 sine theta 2. So all I did was I moved this over because this equation equals 0. And I want to solve this for T1. So let's put sine theta 1 there. Yeah, okay. And then what I get is T1 is equal to sine theta 2 over sine theta 1. I'm going to plug in mg minus T1 cos theta 1 over cos theta 2. But sine over cosine is tangent of theta. So I can actually change this, get rid of this, and just call this tan theta 2. And now if I look at this, what I get is I get T1 mg times tan of theta 2 over sine of theta 1 minus cos over sine means this is T1 tan theta 2 over tan theta 1 cos over that. So this guy I'm saving. And then finally, on a brand new page, let's move that over. I get T1 minus T1 times tan over tan. This is plus, sorry. And that's tan theta 2 over tan theta 1. No, wait, did I do that wrong? Whoops, sorry. Sine over cosine. Is tangent. And sine, yeah, no, I did that. Sorry, I was just double checking my work. So tan theta 2 over tan theta 1 is equal to mg tan theta 2 over sine theta 1. I know this is annoying algebraically. Distributing or pulling a T1 out, tan theta 1 over, or tan theta 2 over tan theta 1 is equal to mg tan theta 2 over sine theta 1. And then finally, T1 is mg tan theta 2 over sine theta 1 divided by 1 plus tan theta 2 over tan theta 1. And so what we get, theta 1 was 20 degrees, theta 2 was 30 degrees, M was 1400 kilograms. On the top, I get 1400 times 9.8 times tan of 30, all divided by sine of 20. So I get 23,160.173. In the bottom, I have 1 plus tan of 30 divided by tan of 20. And that is 2.58625. So 23,160 divided by that answer is about 9,000 newtons. It's a big old annoying mess, I know. There's probably other ways you could shortcut it, but it starts from these two equations, and you need to solve these for T1 or T2 and substitute in, and then eliminate things and solve for the other one. If you do all that, I get this. They did some faster calculations. And you see angle and radians, which is fine. What is the tension in rope 2? And that's easy. If we go back now, we know that T2 sine theta 2 is T1 sine theta 1. Divide both sides by sine of theta 2. T1 was 9,000. Sine of 20 divided by sine of 30. And that's 9,000 times sine of 20 divided by sine of 30. That's about 6,156 newtons, so 6,200, I would guess, or 6,100 is what they're getting. I don't know why they're getting 6,100. Maybe how they rounded it, because it wasn't actually quite 9,000. So 89 times sine of 20 divided by sine of 30. Yeah, I get 6,125 if I do that, which rounds to 6,100 newtons. So they rounded down to 6,100 newtons. They did this the long way, but honestly, once you have these, you could solve this for T2. The hard part is the algebra when you have to solve for everything else. So it's annoying. But FG is mg. They call it the force of gravity. Yeah. So it's a big pain. The one we did on the worksheet was much easier because we had to do less algebra. All right. Now, Sam has a mass of 80 kilograms, takes off across level snow with jet-powered skis. Skis have a thrust, so the skis have a force of 210 newtons, and the coefficient of kinetic friction in the snow is 0.1. Now, that only lasts for 8 seconds, so we want to find the top speed. What's going to happen is, starting from rest, okay, starting from rest, Sam is going to take off. V initial will be 0, X initial will be 0. We don't know what X final is. We don't know what V final is. We do know that the time is only going to be 8 seconds. And that whole time, he's going to have a thrust force, or he, I'm not sure which, of 210 newtons. Now, there is friction the whole time with a coefficient of 0.1, 0.1. And once we find V final, I believe she's going to come to rest, but we'll deal with that in a minute. For now, we need to figure out what is her acceleration. And we do that with a free body diagram. So normal force, we assume mg. We assume that the force is pushing her that way. And if her velocity is going that way, the force of friction is going this way, and it's mu n. So call this direction positive ax. This is ay. And I get may is 0. She doesn't leave the snow. N minus mg, so n is mg. And then in the x, it's the force minus the force of friction, which is mu n, but n is mg. So to find her acceleration, a in the x is f minus mg minus mu mg, all divided by m, divide through by m. Don't cancel anything, just leave it. That is 210 minus 0.1, 80 kilograms, 9.8 over 80. And so A is 210 minus 0.1 times 80 times 9.8 divided by 80, 1.645 meters per second squared. So now we know that A is 1.645 meters per second squared. We don't have X final, so we're going to choose the time. This is our equation for time with constant forces, constant acceleration. V initial was 0, so V final is simply 1.645 times 8 seconds. Multiply that thing by 8. And I get about 13.2 meters per second. Or 13. So we used the free body diagram, found A. We got A. Once we had A, we could plug it into this part. Okay, 13.2. All right. Now, however, how far has Sam traveled? I guess it's a he, before he stops. So now, okay, we want to know, I think they want the full distance. We'll figure it out. So how far did Sam go? Well, x final minus x initial is v naught p plus a t squared over 2. So during the part with the thrust, when a was 1.654 or 1.645 meters per second squared, x initial was 0, v initial was 0, x final was 1.645 over 2 times 8 seconds squared. So 1.645 times a half times 8 times 8, 52.64 meters. Now during this phase, where v final becomes 0 and v initial is 13.2 meters per second, we need to figure out how far he went. V initial is 13.2 meters per second. V final is 0. Time is unknown. X initial is 52.64. X final is what we want. And A now, the only force without the thrust, again, normal and weight are the same, but now the only force is mu n, and our acceleration is that way. So ma is mu mg, or our acceleration, well, negative, is negative mu g. It's in the opposite direction of the acceleration. So our A is negative 0.1 times 9.8, or negative 0.98 meters per second squared. And now we can find x final, use the one without time. V final squared minus V initial squared is 2a, x final minus x initial. V final will be 0. X initial is going to be that. So negative V initial squared is 2a, x final minus x initial. Divide by 2a, that goes away. Then make sure you add x initial to both sides. And we get x final. Negative V naught was 13.2 squared. A was negative, remember, negative 0.98. And x initial was 52.64. And we get, during the whole trip, 13.2 times 13.2 divided by 2 times 0.98. And then add 52.64 to that. And I get 141.5 meters, or 142 meters. 140 meters, I guess, is what they want. All right. So in this problem, in the initial phase, the force minus mu n was ma. So ma is force minus force of friction. That gave us this acceleration. We use these variables, plug them in, and find v final. In the second phase, v initial was whatever the v final we just found for the first part. V final was 0 because he goes to a stop. X initial is wherever he ended up. So you needed to actually calculate what x final was, but you had time, so it's not hard. And then we're going to find x final for the second phase. The acceleration is simply the force of friction because there's no force, and it's negative because it's opposite of the direction of the velocity. It's not too bad, not too bad, I don't think. But yeah. All right, now this one is actually kind of fun. We have a force that we can exert of 6.8 newtons on either side of the object as shown. Now there's a coefficient of static friction of 0.74. So let's think about this. Now, we're holding this book with our fingers. So our fingers are holding this book. There's a normal force on the book. This finger is pushing it that way, and that's a normal force. And this one is pushing that way with another normal force. Those two normal forces are equal to 74 newtons, I think it said. I'm sorry, 6.8 newtons. So the normal force on each side is 6.8 newtons. But now as we look at this, there's going to be a force of static friction trying to keep it from falling that is equal to mu n on both sides. So there's a force upward and there's a weight downward, mg. These are both mu n. Okay, we know that mu, the static friction coefficient of 0.74, 0.74. What it wants to know is how heavy, what is the biggest mg you could hold? How big can this be? Well, if we let the acceleration be upward, it's going to be 0, but MAY is 0, is 2 mu n, where n is 6.8 and mu is 0.74, minus mg. So the heaviest weight we can hold, the biggest mg can be, is 2 mu n, or 2 times 0.74 times 6.8, which is 2 times 6.8 times 0.74, which is about 10 newtons of force. If I divide that by 9.8, it's about 1 kilogram of mass can be held by your fingers. So just, it's a cool problem because it's an easy problem, but understanding that the friction force goes up because the weight's trying to make it drop. And the friction force depends on the normal force that your finger can push on it. It's kind of a cool problem. I like it. All right. And then finally, we have drag. And if you remember, man, it feels like forever since we did drag. When an object is freely falling, it has a force of drag and it has a weight, mg, and then it has an acceleration, which we can say is down if you want. So MA is mg minus FD. But our force of drag is C, which is just some coefficient based on the object, rho, which is the density of air, This, I told you guys in class, to use a half. The density of air is 1.2 kilogram meters cubed. Cross-sectional area. And finally, V squared, and the whole thing is divided by 2. So this is the force of drag, one model for it. Now, if it has a terminal speed of 12, and it's a 6.5 centimeter ball. Now a ball, when you're looking at it straight on, a ball looks like a disc, and a disc has an area of pi r squared. This whole area is pi r squared. It just, that's how it interacts with the air as it falls. The air sees it as just a circle with an area of pi r squared. So that's our AX. We were asked to find what is the ball's mass, okay? So at terminal speed, mg equals FD. And that means that m is equal to C rho AX V squared over 2G. If I use a half, this is 1/2, and I might have that wrong, divided by 2, times 1.2 times pi. Now we were given the diameter in centimeters. Diameter is 0.065 meters. Half the diameter is the radius. So pi r squared is actually pi d squared over 4. Plug in d over 2 here and square it. So this is pi times d divided by 4 squared, and d is 0.65 squared. And then v, we're told, was 12 meters per second. And that becomes squared, and then 9.8. So we have 0.5 times 1.2 times pi divided by 4 times 0.065 times 0.065 times 12 times 12. Divide all of that by 2 times 9.8. And we get the mass is 0.014. I may have that C wrong. Nope. I get 1.46. I had it right. This is about 15 grams. Remember, there's 1,000 grams in a kilogram. So if I round up, this is 0.015 kilograms or 15 grams divided by 1,000. So yeah, that's so the deal is the drag force is 1/2 CP or C rho A B squared. At terminal velocity, the drag force is equal to mg because it's not speeding up anymore. It has no acceleration. So you can set mg equal to this. C has to be 0.5. The half is another 0.5, or this is a 0.5 out front. This is C. C is a coefficient that depends on the object, temperature, all sorts of stuff. It's an experimental coefficient. Rho, this little p looking thing, is the density of air, and air is usually about 1 kilogram per meter cubed. A is the cross-sectional area, so as you would see, it's a shout at it, pi r squared. But we were given the diameter, not the radius. So you need to take the diameter of 0.065 meters divided by 2, and plug that in. And then v squared, and we were told that v was 12 meters per second at terminal velocity. Setting all that equal to mg means to find mass, take this and divide it by g. And that's what you get. You get 15 grams. So anyway, feels like forever since we did those. Next week, I'm going to get, later tonight, I'll have the practice exam with solution posted, and then we'll get reviewing next week, and we should be good. So I hope you all have a happy, safe, dry weekend, although I bet it's going to rain and snow all weekend. But have a good weekend. Talk to you later.